Here we go. We have problem number 4 for this property of materials section. So we have a tube that is submitted to a force, 50 kilonewton, and we record the change in shape. So when we pull on it, we notice that it's elongate of 3.4 millimeters in the length, and the circumference decrease of 0.1115 millimeters. So based on those observations, the question is, what is the modulus of elasticity of the materials? What is the Poisson ratio? And what is the shear modulus of the material? And we can deduce which materials it will be with that if we look at the page, the table at the end, like the table with all the Young modulus and all the information. So let's look at all the formula that we have, or let's try to organize that. We talk about the force, we talk about the modulus of elasticity. So modulus of elasticity, remember the formula with the look O, it's sigma equal E times epsilon. How do we find sigma? Sigma equal the force divided by the area. How do we find epsilon? That will be your delta elongation divided by the initial length. And for the Poisson ratio, the nu equal minus, this is the strain lateral minus the strain lateral divided by the strains normal. Okay, so this one with the strains normal. And for the shear modulus, the formula that we have is the G formula. That is the Young modulus divided by 2 times 1 plus nu. So the only thing that we don't see there in our formula is the E lateral. So the E lateral that will be provided by, let me find a little space to write it. The E, like I call that E, the epsilon lateral, that will be the change of the circumference. So the R, the circumference, the change, let's say the delta circumference minus the circumference initial divided by the circumference initial. Okay, so that will be your change of circumference. The epsilon lateral change in circumference, the epsilon normal change in normal elongation. So we have all those formulas. So let's try to get some of them to start with. The first one, sigma equal E epsilon. We don't have any of this. Sigma equal the force divided by the area. I think this one we can manage it. We have the force 50 kilonewton and the area. Okay, let's find the area. We have the data there for the area. So we have inside diameter. So we have the outside diameter that is 25 and the inside that is 20. So the area will be equal to pi, pi time the outside diameter 25 divided by 2 square minus pi times the inside diameter 20 divided by 2 square. So for the area in millimeter square, we get, how do we get for the total area? Oh, let me find it. This one minus this one, 176.7. 176.7 millimeter square, so that I will plug it there, 176.7. So 50, and that's 50 kilonewton. Let me add the 3,000, the 1,000. That will give us 282.8.9 megapascal. Okay, don't forget your 1,000. 50,000. So this is for the normal stress. Oops. And for the epsilon, formula number 2 for the epsilon normal, so the elongations, we have the L0, that is 800 millimeter, and we know the delta is the 3.4. Oops, 3.4. Millimeters. So the epsilon equals 3.4 divided by 800. 43, does that still record? Yes. Let me add one more number, so we have three significative number. 4 to 5, 4 to 5, and this is millimeters per millimeters. So we have the sigma, and let's put it in red. We have the sigma, and we have epsilon. We can find with the Hooke law, we can find the Young modulus. So we have E equal sigma divided by epsilon. So this is the 282.9 divided by 0.00425. And you say, oh, that will be big. Yes, but usually it's gigapascal. So E equal 66,575 megapascal, or that's 66.6 gigapascal. Hey, based on that, if you look at your informations like your ABAC with the gigapascal, or the 60, you can check around that, but that could be, mm, I'm looking at this. That would not be the glass, of course. Oh, that's way more than that. That could be some aluminum. Aluminum is around 70 gigapascal. So that could be aluminum, for example. Okay, so we answer the question for the modulus of elasticity. So step number 2, so that was number 1. Step number 2, we want to find the Poisson ratio. So the Poisson ratio, we already have the E normal. We need to find the epsilon lateral. Okay, so what we know is that we know the circumference. So before the circumference around, that was pi times 25, the pi times the diameter. And now the circumference is a little bit smaller. It's pi times 25 minus 0.115 millimeter. Okay, I need to make a little change. When I wrote that, I was just realized it's not the E lateral, this formula there. There is no circumference there. It's just the delta circumference divided by the circumference. Remove that. Okay, this is correct now, like this. So that will be just the delta of the circumference divided by the circumference. So just the change. Here we go. So the epsilon lateral equal 0.115 divided by pi times 25. And this is negative. This is a decrease. The circumference is decreasing by minus 0.115 millimeter. Yes, millimeter. So this gives us E lateral equal minus 0.001464 millimeter per millimeter. And now we can plug that in the Poisson ratio equal minus the minus E lateral divided by the E normal. So this is minus 0.001464 divided by the E that we found before, 0.00425, and we found a Poisson ratio of 0.345. There you go. Let me highlight this answer. And last step, we want to find the shear modulus G, so that's step number 3. And G, we have the formula to the left. That's the modulus Young divided by 2 times 1 plus nu. And this is G equal 66.6 divided by 2 times 1 plus 0.345. Your Poisson ratio is always positive, always. So we got G equal 24.8 gigapascal. Here we go for the shear modulus. So write all your formula We have sigma equal E epsilon. We know the formula for sigma. We know the formula for epsilon. We know the formula for the Poisson ratio and the formula between the shear modulus and the Young modulus and the Poisson ratio. And that was the E normal, epsilon normal, and that was the epsilon lateral. Always the little change divided by the original length or circumference or dimension. Hope everything makes sense. Bye bye.